Hello and welcome back to our cryptography course. Today I'm going to talk about hybrid encryption, which is an efficient and resource-saving way of using public key encryption. As a supplementary read for this segment, I recommend Katz-Lindell chapter 11.3. One aspect of public key encryption we haven't considered yet is that it is expensive. In particular regarding the computational overhead of encryption and decryption. Roughly, in practical terms, public key encryption is 2 to 3 orders of magnitude slower than private key encryption. As a ballpark, software implementations of AES achieve an encryption rate of around 700 megabytes per second and core. Compared to that, our modern RSA implementations just achieve encryption rates of 1.5 megabytes per second. So the question is, how can we efficiently encrypt large amounts of data? The answer to that is hybrid encryption. Combine public and private key encryption to get the best of both. How do we do this? The idea is as follows. For every new encryption, let's say we want to do a public key encryption of a large file, for every such encryption, first generate a fresh key K for a private key encryption scheme. Now use this key K to encrypt a message M, and think of this message M as rather large. So we encrypt this message M using the key K, obtaining a ciphertext C2, and we call this the payload ciphertext. And finally, we encrypt this key K under a public key encryption scheme using a PK into a ciphertext C1. And our final ciphertext consists both of C1, which encrypts the key K, and C2, which encrypts the message M under the key K. The advantages of hybrid key encryption are almost immediate. The key K is short. Typically for AES, the secret key is of size 256 bits. Thus, the expensive public key operations, encryption and decryption, are only performed for a very short message. So we only need to encrypt 256 bits using this expensive operation. And the bulk of work is performed by the fast private key encryption scheme. Also, as an additional bonus, this typically minimizes the size of the ciphertext for large messages. The constructions of private key encryption that we've seen recall the modes of operation for block ciphers. For private key encryption constructed this way, the size of the ciphertext is essentially the same as the size of the message it encrypts for a large message. Recall that in the modes of operation of block ciphers, the only additional information we have to send along is the initialization vector. So using hybrid encryption, we can also save communication bandwidth. Whereas if we compare this to the El-Gamal encryption scheme, there to say encrypt a message that is of size 1 group element, say 1024 bits, we had to send 2 group elements, that's 2048 bits. So with plain El-Gamal encryption, we actually pay a factor 2 in bandwidth. Okay, now as I just explained, for private key encryption, the size of ciphertexts is roughly the size of the message. Let's consider this in an example. let's say you want to stream your favorite movie from Netflix. And the way this can be done is that Netflix first sends you a key K encrypted under your public key, and then sends your large movie or streams the movie using or encrypted using this key K. So that's kind of the setting we like to think about when we talk about hybrid encryption. We want to think that the actual message we want to send is a large amount of data, such as a movie that we want to stream. So looking at this, the overall ciphertext rate, which we can define as the size of the ciphertext divided by the size of the message, is for hybrid encryption. Well, we said that the private key part of the encryption is roughly the same size of the message that it encrypts. So really the only overhead we have to pay is this additional ciphertext C1, which encrypts the key K. But we said this ciphertext C1 encrypts only this key K, a small number of bits, 256 bits. So in effect, the overall ciphertext rate we achieve is almost 1 or approaches 1 for long message sizes. So if this size of M is, let's say, 10 gigabytes or 5 gigabytes for a movie, and this C1 is just 256 bits, this is a number very close to 1. But if we briefly think about how we use our public key encryption scheme here, our public key encryption scheme doesn't need to be capable of encrypting arbitrary messages. It just has to be able to encrypt randomly chosen or somehow randomly generated keys. So when we use public key encryption this way, the ciphertext C1, the public key ciphertext, merely encapsulates such a randomly chosen key K. This leads to the idea of key encapsulation mechanisms, which we can think of as a simplified form of public key encryption, a form of public key encryption with somewhat reduced functionality. So what we do here, in a key encapsulation mechanism, we replace the encryption algorithm of public key encryption by an algorithm which generates a key K together with a ciphertext C, which encrypts or encapsulates this key K. Way we can think about this, the encapsulation algorithm takes as input is a randomized algorithm which takes as input a public key, outputs a ciphertext C1 and such a uniformly random key K. And of course, now we can use this key K in our hybrid encryption construction. That is, we can use the key K to encrypt the payload message M. And typically, this allows for a small, say, factor of 2 size and efficiency improvement as I said earlier, the ciphertext doesn't need to encode arbitrary user-chosen messages, but somehow just has to encode or encrypt a random or a random-looking key K. So let's briefly fix the syntax of key encapsulation mechanisms. A key encapsulation mechanism, or KEM, consists of 3 PPT algorithms: keygen, encaps, and decaps with the following syntax. Keygen keygen has the same syntax as the keygen algorithm of public key encryption, in that it is a randomized algorithm which takes as input the security parameter and outputs a pair of public and secret keys PK and SK. The NCAPS algorithm is a randomized algorithm which takes as input just a public key and outputs a ciphertext C and a key K. The DCAPS algorithm is a deterministic algorithm which takes as input a secret key SK and a ciphertext C and outputs a key K. As always, the most basic property we require is correctness. So we require that it holds for all security parameters lambda that if we first generate a pair of public key and secret key via keygen and C and the key K via the NCAPS algorithm, and then decrypt the ciphertext C, we get the key K, or the same key K that was produced by the NCAPS algorithm with probability 1. So decapsulating this ciphertext yields the same key that was produced by the NCAPS algorithm. In terms of security, we will require or define chosen plaintext security for key encapsulation mechanisms similar as for public key encryption. So the INCPA experiment for chems is defined as follows. As always, we have an adversary A and a challenger. Now the challenger generates a pair PK-SK of public and secret keys for the chem. Then it runs the NCAPS algorithm, which produces a challenge ciphertext C ast. Then next it flips a bit B. If B equals 0, it sets the challenge key to be the same key that was produced by the NCAPS algorithm. But if B equals 1, it just chooses this challenge key K ast uniformly random and fresh. Now it sends public key, challenge ciphertext, and challenge key to the adversary. And of course, the adversary now has to guess the challenge bit. Outputs a guess B prime. And if B prime equals B, where B is this challenge bit, we say the adversary wins, otherwise he loses. So in a way, this INCPA security experiment for chems asks that a key K produced by this key encapsulation algorithm is pseudo-random given both the public key PK and the ciphertext C ast encapsulating this key. The definition, or the final definition, asks or says a chem keygen NCAPS DCAPS is INCPA secure if it holds for every PPT adversary A that there is a negligible function nu such that for all security parameters in N we have that the probability that A wins the INCPA experiment is at most 1/2 plus nu. Now that we have defined key encapsulation mechanisms, let's briefly look at two examples. First, of course, there's the trivial chem, where we just use a public key encryption scheme to encrypt a randomly chosen key K. So key generation for this chem is the same as for the underlying public key encryption scheme, and we encapsulate a key K by just choosing K uniformly random from 0, 1 to the security parameter and encrypting it under the public key encryption scheme. And then we output the ciphertext C and the key K. To decapsulate, just compute and output the decryption of the ciphertext C. As a more interesting example, we have that every two-message key exchange protocol immediately yields a key encapsulation mechanism. And let's look at this, let's consider this with the example of the Diffie-Hellman-Cam, or in other words, let's interpret the Diffie-Hellman key exchange protocol as a key encapsulation mechanism. So here the keygen algorithm chooses a uniformly random X in ZP, computes H as G to the X, outputs GH as the public key, and X as the secret key. To encapsulate a key, we choose a uniformly random Y in CP and output a ciphertext C, which is just G to the Y, and the key and a key K, which is H to the Y. To decapsulate a ciphertext C given a secret key, which is just X, we compute the key K by just C to the X. So now for this key encapsulation mechanism, the ciphertext is only one group element, whereas for El Gamal, recall, our ciphertext consisted of two group elements. And in fact, the in-CPA security of this key encapsulation mechanism follows immediately from the eavesdropping security of the Diffie-Hellman key exchange, or phrasing it differently, it follows immediately from the decisional Diffie-Hellman assumption. In order to see this, really just notice that keygen in the notation from the key exchange lecture, the keygen algorithm is the same as the LS1 algorithm, the NCAPS algorithm, the same as the Bob algorithm, and the DCAPS is the same as LS2. In that way, security of this key encapsulation mechanism follows immediately from the decisional Diffie-Hellman assumption. We will now show that the construction we discussed in the beginning of this lecture actually yields an in-CPA secure encryption scheme. So first, let's write down this construction formally. So assume that keygen NCAPS and DCAPS is a key encapsulation mechanism and EncDEC is a private key encryption scheme, which for simplicity just uses uniformly random keys. Now we can construct a public key encryption scheme, keygen prime, enc prime, dec prime, as follows. So keygen prime just computes keygen, the keygen algorithm for the key encapsulation mechanism. Enc first encapsulates a key or runs the NCAPS algorithm, obtaining a ciphertext C1 and a key K. Then it uses the key K to encrypt the message M under the private key encryption scheme, obtaining a ciphertext C2. And the final ciphertext C is just the pair C1, C2. To decrypt such a ciphertext, first we decapsulate the key K using the DCAPS algorithm on C1, and then we compute and output the message M by just decrypting C2 using the key K. And we have the following theorem. Assume that keygen NCAPS DCAPS is an in-CPA secure key encapsulation mechanism, and further that EncDEC is an insecure private key encryption scheme. So we don't need INCPA security, we just need insecurity, a ciphertext only indistinguishability security. Then the public key encryption scheme keygen prime, enc prime, dec prime is an INCPA secure public key encryption scheme. So let's go into the proof of this. As always, assume A is a PPT adversary with non-negligible advantage epsilon against the int CPA security of keygen prime, enc prime, dec prime. Now, our goal, show that this implies that either keygen, ncaps, dcaps is not INCPA secure, or EncDEC is not insecure. Secure. Okay. As always, let's first write down the INCPA experiment for the scheme keygen prime, enc prime, dec prime. And let's call this experiment exp for short. Okay, as always, we have our adversary A. And a challenger. And of course, the challenger first generates public and secret keys. And gives the public key to the adversary A. Whereupon the adversary A announces two messages, M0, M1. The challenger flips a uniformly random bit B and encrypts the message MB. And how do we encrypt it? Well, we first compute C1, comma K via ncaps. And C2 as an encryption of or an encryption using the key K of the message MB. So next thing we're giving this ciphertext C, which just consists of C1, C2 to the adversary A. And the adversary A outputs a guess B prime. And of course, if B prime equals B, we output 1, otherwise 0. Okay, that's our in-CPA experiment for this scheme. And as always, when we prove security using several assumptions or several building blocks, we will go through, or we'll at least once modify this experiment into, say, a thought experiment or a hybrid experiment. And the way we will do this here, call this new experiment exp prime, will be by the way we compute the ciphertext C2. So instead of using the key K, we will just choose a fresh and uniformly random key K-ast, and use K-ast to encrypt the challenge message MB. So that's the only modification. We change, or we sample a fresh key K-ast and use K-ast to encrypt the message MB. Now I claim that the winning probabilities of A in exp and x prime in the unmodified and modified experiments are essentially the same, or stated differently, probability that he wins in x prime minus in exp minus probability that the adversary wins in exp is negligible. Let's quickly see how we can prove this claim. So we go into the proof of the claim. Now, of course, this also works via a proof by contradiction. So assume towards contradiction. That probability x prime equals 1 minus probability exp equals 1 is greater than epsilon prime for a non-negligible epsilon prime. And what we will do is we will construct a PPT adversary A prime with advantage epsilon prime against the in-CPA security of the chem. Okay. How are we going to do this? Our adversary A prime looks as follows. So A prime is an adversary against the in-CPA security of the key encapsulation mechanism. So its experiment gives it as input let's say pk c1 and a key k asked. This is what its challenger provides it as input, right? So, but what does a prime do? Well, now, of course, a prime simulates the experiment exp. How do we do this? So first, it gives the adversary A the public key pk, which directly comes from its own input. Next, the adversary A outputs two messages M0, M1, whereupon A prime, still simulating the INCPA experiment or the experiment exp, flips a uniformly random bit B and encrypts the message MB using key K asked, where of course K asked comes from its own input. This gives us a ciphertext C2, and now we just set C to be C1 asked, or C1, sorry, let's call this C to the C asked is C1, comma C2, where of course C1 comes from the input of A prime. Now we send this C asked to the adversary A, whereupon the adversary A outputs a bit B prime, and if B prime equals B, our adversary A prime outputs 1, otherwise 0. Okay. Good. And this is the output, let's call it B double prime, that goes to its own challenger. Okay, so that's the description of our adversary A prime. Now let's see, or let's compute the advantage of this adversary A prime. Now to do so, let B asked be the challenge bit of A prime's challenger. Okay, and we will distinguish two cases. Case 1, we just have B asked equals 0. In this case, we have that the input that this case input pk c1 k asked of A prime was computed by, well, PK is of course the output of a run of the keygen algorithm, but C1 and K asked are the result of just computing the encapsulation algorithm on PK. But what that means is that our A prime, in fact, faithfully simulates the experiment exp, which is just the standard INCPA experiment for keygen prime, enc prime, dec prime. So faithfully simulates exp from the view of A. And this means that the probability that our A prime wins the INCPA experiment A equals 1 conditioned on BS equals 0 is the same as, well, probability exp equals 0, which is that the probability that A loses the INCPA experiment, right? Because our A prime, sorry, this is an A prime. A prime, if BS is 0, A prime wins the INCPA experiment if it outputs 0, but it outputs 0 if our algorithm A outputs the wrong answer. That happens, or that's exactly the case when exp equals 0. In the second case, of course, it holds that B asked equals 1. That is, our PK C1 comma K asked is computed by first C1 comma K is computed by running the ncaps algorithm on PK. And then we just choose ourselves a uniformly random and fresh K asked. And in this setting, we immediately see that, or in this case, our adversary A prime faithfully simulates X prime from the view of A. Why? Well, because all messages that A gets in the simulation have the same distribution as in X prime, right? The only difference essentially being the way the key K asked was chosen, that now it's being chosen uniformly random instead of taking the key k that was produced by the NCAPS algorithm. Okay, so we have that. The probability that our A prime wins the INCPA experiment conditioned on B asked equals 1 is the same as, well, probability that A wins the experiment X prime. Okay, now we're almost done. Now we know the winning probability of A prime conditioned on B asked equals 0 and on B asked equals 1. But because I need some space, I'll go to the next slide. So we conclude that probability int CPA A prime equals 1 is of course just by the law of total probability, our friend. 1/2 times probability int CPA A prime equals 1 conditioned on B asked equals 0 plus 1/2 times probability int CPA A asked equals 1 conditioned on B asked equals 1, where of course this 1/2 here is the probability that B asked equals 0, and this 1/2 is the probability that B asked equals 1. So from what we just computed, this probability here is the same as probability exp equals 0, and this probability is the same as probability exp prime equals 1. So, but since exp is a random variable which can only be either 0 or 1, therefore the probability that exp is 0 is of course 1 minus probability exp equals 1. Okay, so we can rewrite this as 1/2. This comes from this 1 plus 1/2 times probability x prime equals 1 minus probability x equals 1. But here, this of course we know is greater than epsilon prime. So altogether, this is greater equal 1/2 plus epsilon prime half, which of course contradicts the INCPA security of chem. Contradicts int CPA security of chem. Okay, so let's go to the next slide. Consequently, we have that under the assumption that our chem is INCPA secure, we have that probability that x prime equals 1 is greater than 1/2 plus epsilon minus negligible, right? And this 1/2 plus epsilon, this is just the probability that x equals 1. Okay. And we will now show that this implies a PPT. Maybe first, let's call this expression here epsilon double prime. This is 2 primes. We will now show that this implies a PPT adversary, a double prime with advantage epsilon double prime against the insecurity of EncDEC. Security of EncDEC. Okay. How does this adversary a double prime look? Well, of course, as always, this is nothing new. It will simulate the experiment X prime for not good, for the adversary A. So first, it's gonna generate a pair of public and secret keys, PK and SK, for using the keygen algorithm of the chem, of course. Gonna give PK to A, and of course A will answer with 2 messages M0, M1. So here's the challenger of A double prime. And of course, A double prime will just forward its 2 challenge messages M0, M1 to its own challenger, upon which the challenger will answer with a challenge ciphertext C, let's call it C2 ast, which is either an encryption of M0 or M1. It's an encryption of MB, where B is the challenge bit, and C2 ast is an encryption of using some uniformly random key K. We encrypt MB here. Okay. So now all our adversary A prime has to do is, let's call this key K ast, is run the ncaps algorithm and set C to, or C ast to C1, comma C2 ast, where of course this C2 ast is taken right from this input here. Now C ast is given to the adversary A, which of course responds with a bit B prime. And all our adversary A double prime is gonna do, it's gonna forward this bit B prime. That's already the entire description of this adversary A double prime. And looking at this simulation, we see that from the view of A, A double prime simulates X prime faithfully. Why? Well, first observed that PK, SK, of course, have the same distribution, but then, of course, also the challenge ciphertext C ast has the same distribution as in exp prime. Therefore, it follows that probability that our adversary A double prime wins the int experiment is precisely the same as of course, that the probability that A wins the exp prime experiment. Here we said that this is greater than 1/2 plus epsilon double prime, where epsilon double prime was something non-negligible, but this contradicts the insecurity of the private key encryption scheme EncDEC. Okay, so this concludes this proof. And it's time to wrap up this lecture. We have seen that hybrid encryption combines the advantages of both public and private key encryption, in that the public key part is only used to transport a key for the private key encryption scheme, and the actual payload message, which we imagine to be something really large, is encrypted under the fast private key encryption scheme. For long messages, and think such as settings where we want to stream movies, this is essentially as efficient as private key encryption, both in terms of the ciphertext rate and the encryption overhead. And finally, key encapsulation mechanisms, KEMs, provide an efficient way to encrypt a random key that we will use in hybrid encryption. Okay, that's all for today. Thanks for watching and goodbye.